Now, we can look at the difference between the two regions. And we can see that there's going to be a higher potential area and a lower potential area. So the difference between them is going to be called the potential difference. Or other people are going to call that the electromotive force, or EMF for short. So when you go to physics, I think a lot of times they'll be talking about a cell EMF. A lot of chemists, when they do electrochemistry, they talk about just cell potential, which is short for the potential difference between the two half cells. So we're going to represent either the potential difference or the electromotive force with a capital E with a subscript cell for essentially the cell potential. And we're going to measure the cell potential in units of volts, or a capital V. Now, because this will come up a little bit later, 1 volt is the same as 1 joule per coulomb. So joules is a unit of what? Energy. So you can get excited about the fact that we're going to relate cell potentials to energy, which we just finished talking about in chapter 19. Standard reduction potentials. I knew that was going to happen. Now, the standard E cell potential is going to depend on the half reactions that are involved. So we did a voltaic cell with zinc and copper, for example. If we'd have changed out the zinc and put hydrogen in there with the copper, then that voltaic cell would have a different cell potential than the zinc-copper reaction, just because there's a different combination of half reactions involved. The reduction potentials, and now this is where I differ a little bit from some of your slightly older than me faculty. I go along with the textbooks that we use these days that generally show reduction potentials. Some of the older faculty, when they were learning electrochemistry, they learned oxidation potentials instead. So they learned their reactions backwards from the way we learn them today. Various pedagogical reasons for doing that, but I'm going to stick with what the textbook does, which is reduction potentials. So reduction potentials are going to be assigned relative to the hydrogen half reaction. So if we have 2 hydrogen ions being reduced by reaction with 2 electrons, we get H2 gas at 1 atmosphere pressure. And that, by definition, the reduction half potential for that reaction is defined to be 0 volts. So there's no reason that we couldn't have established a table of reduction potentials with some other reduction reaction being assigned to 0, but we needed somewhere to start. And hydrogen, this reduction is kind of a nice medium reaction. There's some that are a lot more easily reduced, some that are a lot less easily reduced. So they just decided that this reaction would be defined as 0 volts. And there are tables of reduction potentials, and so you might want to look at table 20.1 as you do your homework for this chapter, because that involves the reduction potentials for a lot of these half reactions that we're going to talk about. Okay? Now, to find the cell potential, the standard cell potential is going to equal the reduction potential of the cathode minus the reduction potential of the anode. And again, I have to stress that all these are using reduction potentials. I think your lab manual actually has a slightly different version of this equation. I think your lab manual has E cat plus E anode. The reason it does that is because instead of using the reduction potential for the anode, it has you use the oxidation potential. It has you flip around that reaction, and so you flip around the potential. So you come out with the same way, but just be aware that there's a difference between what the textbook and what I show you, and your lab manual is going to show you something different. So you can use either one as long as you're consistent. I like this way because we're only using reduction potentials that we find in table 20.1. Okay? So another important thing to remember when we're doing cell potentials is that stoichiometry does not matter. So it doesn't matter what your coefficient is in front of the hydrogen ions or in front of the zinc metal or zinc ions. That does not change this reaction. You simply look at the cathode reduction potential, subtract from that the anode reduction potential, and that'll give you your cell potential.